Hello everyone, I am Rouxel from the University of Amsterdam. Today I will present you PreGo, a generative methodology for satisfying real-time requirements on COTS-based system. I will first define the methodology and then report its application on an industrial use case. So this work has been realized with different partners from Denmark and Netherlands and mostly funded by the TeamPlay EU project. Our industrial partner, Skywatch, gave us a use case to study, which is an unmanned aerial vehicle. So it's a fixed-wing drone that fly above the sea to detect lifeboats. Upon detection, a rescue team is contacted. This use case requires to record videos and images at 2 frames per second. It always detects in the widest possible area, and they want to limit the false positive, which is detecting an object when there is no object, and limit the false negative, which is missing an object. And they also want to be able to relaunch some part of the software if this part crashes. You can see some images from testing the use case. So they have to fly the drone on dry land, as getting authorization to fly above the sea is more difficult. As if you manage to spot the 2 orange spot on the below picture, then you'll see the canoe in the field. This system is composed of 3 bricks: the flight control, the search and rescue, and the image capture. The flight control sends Mavlink messages through a serial port to the search and rescue part. This search and rescue also received images from the image capture through the Ethernet port. Each of these bricks has its own platform on which they run. So we have a Pix Hawk2, for the flight control, we have a TK1 that I will detail a bit later for the search and rescue part, and we have LFL boards and LFL camera for the image capture part. We will mainly focus on the search and rescue part, leaving the 2 other bricks out of the scope of this study. So for the search and rescue part, we are running the software on an Apalis TK1 provided by Toradex. This board features 4 ARM cores, a Kepler GPU, and 2 gigabit of RAM. It also has a power dissipation of 3 to 15 watts. It has been selected by our industrial partner because it's performant, it's embedded oriented, it has a low energy consumption, and a 10 years life support. On this platform, we can run a Ubuntu provided by Toradex with the NVIDIA CUDA driver. The problem with this board is that we cannot easily run an RTOS to meet our timing constraint, and mostly because we need the JStreamer and the CUDA driver for detecting boats on images. To reach some form of timing control with such a difficult system, we devised a methodology that from a legacy software or a newly designed one can reach the goal of a final executable that respect the timing constraint. In this methodology, we have several steps where some are manual and some are automatic. While for the manual mode, they are usually heavily connected to the use case understanding and cannot be automatized, like identifying the worst case execution time behavior, which depend on some constraint of the project itself. And then we will apply this methodology on the industrial use case that I mentioned before. The first step of our methodology is to identify the worst case execution time scenario. So looking at the specification of our industrial use case, we see that it can fly at 1,000 meters above ground and therefore detect objects with a minimum size of 0.5 square meter. At 2 frames per second, and we consider that there is boats in every frame for this worst case scenario. And then we had to look at our partner's code to determine if the number of pixels for an image or for an object, or where the objects are positioned in the image, are actually part of the worst case scenario. Well, in our case, it's only the number of objects that are part of the worst case scenario. So we firstly derived an image with the worst case number of objects in the image, considering 0.5 square meter per object. This led us to an image with more than 4 million objects on an image, which is absolutely unrealistic. Therefore, with our industrial partner, we divide that we should take the biggest cruise ship on Earth and look at the number of flyboats they can embed in this boat. And then we handcrafted an image with 500 boats, which is the capacity of this big cruise ship. So we took their application, executed on the selected platform, and observed the time required to process a frame. So to reach a 2 frames per second frame rate, each frame should be processed in a maximum 0.5 seconds. So here you can observe that we need more than half a second most of the time, that the execution is not stable, and that leads to an overconsumption of the memory. So at some point there will be no more memory and the drone will crash. We also measured the energy consumption per frame, and we are here at 3.8 joule per frame in average. What we want now is to enforce the timing requirements and do not overconsume the memory and reach the 0.5 second deadline. The first manual optimization we applied to increase our control on time is to tame our Linux-based OS. Linux is known to not be the best OS when dealing with real-time system, but it's a constraint of this project that we can't get rid of. Therefore, we configured it in a way that helps us to regain some control on time. The idea is to remove as much interference as possible, this interference coming from the kernel task and the system task. So we first disabled all unnecessary services, then we configured as much as possible internet handlers to use a separate reserved core that will not execute our real-time tasks. And we disabled RT-throttling to prevent the kernel from periodically preempting our threads. You can find a full list of configuration levers to pull in our paper targeting general Linux-based systems and our specific platform. Then we ran the application a second time, and similarly we observe what is the processing time per frame. As you can see, it's more stable, we have fewer deadline misses, which leads to less consumption of the memory. So this execution can be good for soft real-time, but we want to reach hard real-time, so no deadline miss at all. But the drawback here after Taming Linux is that we increased the energy consumption per frame from 3.8 to 4.9 joule per frame, which is not very good when we are on a drone which is battery powered. The next step of our methodology is to identify the task. For that, we looked at the code provided by our industrial partner, and we identified 4 tasks. One is the detection part that will detect objects in the frame. The second one is not the brick of the system for the flight control, but it's the part of the software on the search and rescue brick that will handle the Maverick messages received from the flight control part of the overall system. And then we have 2 JStreamer pipeline that will receive the images and videos from the third part of the system, which is the capture image. So we did some re-engineering by isolating the code of each task. We also created a high-level representation of the application using a domain-specific language of our design that we described in a previous publication. Here you have a small example of what it is. I encourage you to go read our previous publication if you want to have more detail on this DSL. After manually re-engineering the application, we can now enter the automatic steps of our methodology. We developed a tool that takes as input a coordination file written with our DSL that I mentioned before, and a configuration file describing the work that must be done by the tool. Our tool is like a compiler. It first parses the input file and generates code. The generated code, that I will detail a bit more on the next slide, can then be compiled and linked with the identified task code to generate the final executable binary. So the code generation here is to generate the profiling code. This profiling code is a sequential version of the application. We generate the main function, all the FIFO buffer management for the transmission of data between the node of the graph of the identified task. You have an example here where we have the main code with a loop that iteratively and sequentially call the different tasks and subtasks of our project. And this code can be used with Pagh Profiler, a tool from one of our partners, to estimate the energy consumption of the application and to estimate or to measure the execution time of each individual part of the software. Then after executing the profiling code, we can go back to our toolchain and execute it again, but this time taking the scheduling policy generator branch and using the timing and energy information that we gathered from the profiling code. And we can generate a second version that will be the final application. Regarding the scheduling policy, we selected the one that allows us to increase our control on time. We selected one that is partition, without migration, with fixed priorities, and non-preemptive. For this scheduling policy, we have a schedulability analysis created by Akesson in 2019 that we implement in our toolshed, which allowed us then to check the validity of our application regarding the schedule. Then, to deploy the schedule, we have some obvious configuration on the OS that to enforce the partition, we need to set the affinity of our threads. We have one single core map per thread, etc., etc. Then, we regenerate the final code. So basically it's the same as the profiling code, except that this time it's not a sequential version, but a parallel version. And so we also generate all the code required to manage the thread and the processes and the synchronization between the task and subtask. We finally completed all the manual and automatic steps of our methodology PreGo. As you can see on this picture, the execution of the generated code with the proper scheduling policy gives us a far more stable execution time per frame. We have no more deadline misses, and the memory is not anymore crazily increasing. We even managed to reduce a little bit the energy consumption required to process each frame. Using PreGo to increase the control on time with application not initially designed with real-time constraint in mind is therefore a success. As a future work, what we want to do is in the code generation, we want to improve the task management and also include some multi-mode scheduling. We want to improve the energy management by creating a specific tailored scheduling policy that will account for both energy and time while scheduling an application. In this presentation, we describe the application of the PreGo methodology that we define. This methodology requires to perform several steps, which are manual at the beginning and then automated with our tool. This methodology can benefit from real-time system designer to regain control on time with platforms which do not appear optimal for real-time systems. Finally, you can find the code of our tool in the Bitbucket repository written on this slide. And if you have any further questions, feel free to contact us. Bye-bye and enjoy this virtual event.